Welcome to today's Tech Talk about debugging. It's my great pleasure to have Suyash here with us. He's from ARM Forge. Well, he's from ARM, and he's going to present ARM Forge and especially DDT. And then I will present a few things that I did with DDT on ICON. And this whole thing came up a couple of weeks ago when I applied DDT to a bug in ICON, and then said, well, we should do a talk on this, and suddenly I ended up giving the talk on this. And I'm very happy that Suyash, is somebody who knows DDT way better than I do, is going to do the start, and then I'll just show a few things that you can do on the standard model on our computer. So Suyash, the floor is yours.
Thank you, Florian. Hi, everyone. Good afternoon. Hope you're all doing well, and there is some excitement to know about ARM DDT. DDT stands for Distributed Debugging Tool. So the focus of this talk will shift to debugging once we have covered the overview for ARM Forge, which is a suite covering all the HPC tools. So DDT is as I said, distributed debugging tool available for scalar, multi-threaded, and large-scale parallel applications. And going ahead, we'll have a look on all the aspects of debugging with DDT. A little bit of introduction about myself. So, as Florian said, my name is Suyash Sharma, working as a senior applications engineer with ARM Linux HPC software support team, and I'm based in Manchester, UK. I have a bit of a background in CFD with obviously HPC involved. We do have a few more hands in the team, and we work in tandem with engineering and development team, the product team, and you can reach out to us on this email alias, support@hpcsoftware@arm.com. Looking at the course objectives, the talk objectives, we'll go through the overview, and then which covers all the three tools in the suite, and then we'll move on to DDT. So we have divided the talk in two parts. I am taking care of the first one, the first two, and I assist Florian in the debugging, and we'll have a Q&A if there's enough time. To give you a bit of a background on what ARM Forge is, so it's ex-Olenia tools, which was called Olenia Forge, which was a leading toolkit for HPC application developers. It's available on over 65% of top HPC systems, top 100 HPC systems. It's designed in a way to maximize application efficiencies on HPC systems, where you can also use performance reports to design, as best as you can your applications. A quick mention to ARM Forge's history. The software was originally from Olenia, which was acquired by ARM in December 2016. It was a very popular HPC application development tool for the community, and we designed the tools to fit into the development cycle. Since the merger with ARM, the commitment to supporting Forge tool for all HP systems and not just ARM architecture has remained intact. So this is the way to gain trust in the community, and our engineering roadmap is aligned with all the changes in the architecture or the upcoming architectures, including the Cray systems and all the Intel architectures. So there's no foreseen change in this, and we'll continue to support cross-platform in the future. Just a bit of intro on Forge licensing. So Forge can be licensed alone for any architecture platform. So it's part of, it's now a very important part of the ARM server and HPC development solutions. So we call it ARM Olenia Studio. So where ARM has the code generation solution with ARM compiler for Linux. Since ARM has originally wrote software tools like compilers, libraries, and emulators for this module, and performance engineering solution with Forge, which has DDT, map, the profiler, and the performance reports for creating a profiling report. You can also license ARM Forge in itself without going for the whole studio, or you can also actually get one of the tools only from the ARM Forge umbrella. So the licensing has been kept flexible, catering to the particular needs of the community. For a typical HPC application, let's say something very similar to your application, weather forecasting or climate modeling, there's a trend that scientists are working on predicting the weather at smaller and smaller scale. Also the case with ICON. So it's about getting more accurate and precise forecasting results that can benefit everyday people and also the industry. But however, when you reduce the mesh size in this forecast modeling, generates a problem of that at high resolution, additional factors, they greatly impact the outcome of the calculation. For example, finer granule of the ground color, or in which case you would bring more challenges to the supercomputing system. So some of the challenges like scalability, efficiency, need for additional data storage, need for models capable of taking into account added complexity, and a computing power that is suitable to handle all these additional factors. So the tools have been designed to tackle all the three fronts, on all three fronts, scalability, efficiency, and simplicity. So ARM DDT, starting with debugging, is a fast and powerful, easy to use graphical debugger. So the keyword here is graphical debugger. So unlike GDB or the traditional valgrind or print statements, we have a lot of graphics here to explain you the information in as understandable manner as possible. It provides a complete solution for finding and fixing problems on a single thread or multi-threaded application on thousands of threads. I think with ICON for DKRZ, it's about 1,000 thread license. So you can use ARM DDT to debug, let's say, even OpenMP or other parallel MPI software, heterogeneous software, such as those written with GPUs or hybrid codes mixing MPI with OpenMP or MPI with CUDA. You can brute force the code into revealing tricky memory leaks and bugs. Forge in itself as a suite is available on a big majority of machines. A vast chunk, as I mentioned, 65% of top 100, and it continues up till the trend continues up till the next 400. And it's fully supported on ARM on 86. Sorry, supported on both ARM and on x86, IBM Power, NVIDIA GPUs, and also for ARM V8A hardware implementation. Map, on the other hand, is a low overhead profiler with a very small footprint, as it is taking samples from the execution, and it shows you visualized performance data, such as which lines of code took the most amount of time, or compute intensive or memory intensive. And like I said, graphical. So both these tools are designed with an intuitive interface, easy to use for everyone. In the end, we have performance reports that gathers a rich set of data and makes it easy to analyze metrics, performance metrics around CPU, memory I/O, and hardware counters. It tries to build a culture of application performance, efficiency, and awareness. So sometimes you need to monitor and constantly improve the efficiency of your software stack and hardware. And with the performance report, you have the results at your hands without having to spend time or queuing again and again. For example, with map, with the profiling interface. So this adds value to your development workflow with complete automation. How do we access, or how do we run Forge on clusters? So Forge itself is GUI based. So where does it actually run? Well, essentially where the software is running, typically on the compute node. And when you're running a GUI on an HPC system, there can be scenarios where no interactive session is allowed on the compute nodes, or when the system is far away and X11 forwarding becomes really slow. In fact, many of the login nodes in many of the systems that we have come across, they don't even support X11 forwarding. So to provide flexibility to the user, the GUI can be launched in many ways. So with the compute nodes, we have there is an offline mode, or there's also an interactive mode that can be used. And we'll talk about these quickly in coming slides. For interactive mode, you can directly log in on your login node and launch the software. And X11 forwarding, if it is there, it will provide you the GUI. Otherwise, you can also remote launch it in your local machine, in your laptop or your mobile workstation. And again, the forwarding will be connected via a tunnel and SSH tunnel, and there is very little overhead because the software is still being run on the compute node. So all this is right. So this is the login node, and if we reverse connect, we can run the software via the login node, or we can also have remote launch on the machine, and yeah, we can run it with very little overhead. Um, So to launch Forge, one can just simply type Forge. If the module is loaded already, you can just simply type Forge on the command line, or DDT and map as well. With ARM DDT, the target is to run the application code within the debugger. So once you run the application, soon as there is an error, the debugger will stop and it will pause all the processes, the MPI ranks, and will tell you that there is, let's say, segmentation fault in this line, and the process responsible for it is process X. For launching it on your login node, you can just go with DDT -- connect and MPI run or srun, or whichever way you want to execute. You go ahead and this is the GUI that will appear on your system, the control system. For the offline mode, we just prepend the same thing with -- offline, and this will generate a report that can either be a text file or an HTML file, and all the information that I was talking about that can appear in the GUI can also come out in a textual manner in the HTML file. So you have information about messages, output, if you have put any trace points or breakpoints. So all that information is available in the HTML report. So in the same way, there is the option with map. So instead of DDT, we say map -- connect, and as you can see, there is memory usage, MPI call durations, CPU floating points, and if you're using GPU, for example, there's much more information for CUDA GPU, and here you can see your source code, and there is more information about your stacks. So the same way, instead of offline, we have a -- profile, which will generate a profile and save it in your directory. And that profile can be later on opened in the Forge GUI. With performance reports, the data is formatted in a manner that is much more comprehensible. So this is done through a less graphical and more statistical summary of results from the .mat file, and it still manages to include all important aspects of parallel computing results, so highlighting the memory and I/O, the status of your threads, and an overall inference on whether the operations are running memory bound or compute bound. So you have a graphical inference as well, and you can play with it. So this saves a lot of time avoiding queuing. Some more resources are available. For example, the guide, release notes, and also the link to download for the licensing server. So you can access all these documents through these links. And in the end, I will provide a PDF file to Florian to share with whoever wants to have access. And yeah, the links will be there. So coming to ARM DDT, I'll have a little talk about GDB. So Florian told me that a lot of the users in DKRZ are still relying on print statements, and there's not a lot of use of, in fact, even GDB. As a debugger, as an open source debugger, GDB is the most widely used solution. And lately, there's also LLDB with the LLVM. It has been creating some noise as well. But unfortunately, GDB lacks an interactive interface and any sort of comprehensive analysis. It isn't available at your fingertips. On the same line, LLDB is even less interactive than GDB. So on the right, we have the GDB, the interface, and LLDB is even less interactive. So when looking to debug parallelized or vectorized codes, GDB is scalar and doesn't have such powerful options. So it doesn't have multi-language support as well, and also doesn't support heterogeneous computing. But for your distributed programming, we require a debugger that can harness the scaling effect to act more efficient with increasing number of processes and cores, producing little overhead. So you can see here the interface for scalar debuggers. On the right, we have DDT. It's a front end to GDB, and there are, in fact, let's say 20 more other front ends to GDB, but they are just graphical, interface. Whereas ARM, it provides DDT as an answer to the bigger problem of scalability. And it's not just a front end, it's instead a complete software built upon the GDB library, the open source library. So when we talk about DDT, it's not just a graphical transformation of GDB. So developers, they want to answer these questions: who, where, how, why, and ARM DDT is not only able to inspect the code, but it can also force the code to crash, brute forcing. It gathers variable and array values, collects communication data, and the way it presents this data. So there are spark lines that show you value of certain expression for the processes. So the line graph is basically talking about the MPI ranks, and it can show you where the crash has happened on what line number within a particular stack. So we call this smart highlighting, and this is very helpful in answering these three things: who, where, and how. So for DDT, we have, as I mentioned, it collects array values, and you can actually visualize these 3D arrays with a multi-dimensional array viewer, and it's possible for all the main programming languages. So Fortran, C, C++. It supports parallel libraries. It also, because it's highly scalable, so you can also see the value for your array for as high as 1,000 processes. And yeah, as I mentioned, that there's also GPU support. So you can have the same information for a CUDA code. Here you can see the value for your ranks, your different MPI ranks, and the communicator, the queue. So the way the information is highlighted, in this case for the message queues, it makes it easily understandable. So if we talk about the capabilities, I can say sky is the limit here. What we can find out is really too much if you're chasing very deep information. So this is the basic DDT user interface. At the top, you have the MPI ranks. There's a code viewer, and there's the hierarchy. There's also the stacks at the bottom, the local variables for this loop. So whatever line you break at, the local variables for that section of the code will be available here. You can add these to the expressions, and they remain in the evaluate window regardless of wherever you traverse through the code. Also, if your MPI ranks are divided into multiple groups, you can have a visual distinction between group 1, group 2, group 3, and so on. And the number of paused MPI ranks, they are also visible. So you can also switch to threads that I haven't shown here, but there is an option to move to threads, and that will be also shown in the top section. Similarly, you can see here on the right, there are a lot of variables, the local variables, and yeah, you can within the code viewer, you can make changes, you can edit, and you can save it in the actual source code, but you'll have to go back and recompile and launch the session again. It provides you breakpoints, watch points, and trace points as well. So the trace points here, they allow tracing variables, read and write history without needing to stop the application. And the watch points, they will allow observing variables with conditions. So DDT will stop there, and it will emit a notification about the value of the variable when the condition is hit. So at the bottom, you will have all the information for trace points that will also be available in your HTML report. Yep. So in the multidimensional array viewer, you can right-click on an array and select View Array, and this window will appear. And you can also select which particular dimension of the array you would like to view, so you can visualize that data. And the statistics are also available for that 2D or 3D array, and the data table to visualize the rows and columns from different sides. And you can also filter your information, so to show above or below a particular threshold the values or the rows and columns. Oops, yeah. Also, we have this functionality for version control. So you can view version control information for if you have the gate or any other, let's say, mercurial or subversion. So this is available next to your source file, and it's color coded to indicate the age of the source line. Sorry, and there is this line by line information available. Sometimes the debugging exercise can be a little longer and may even go on for a couple of days with a code like yours. And in that scenario, with the logbook, it can help you track your daily changes. So logbook entries provide a track of the historic commands and output values of the current stacks, or whether you have stepped over the process. You can also add annotations to the logbook, and it can be later saved in the HTML file. So you have the option to provide annotation. Yep. We also have a disassembler view. So this 1001 button at the top, it shows the assembly code, and you can also select it from tools, disassemble, and um, for an optimization focused developer, this provides very good insight into optimization, vectorization of the loops by the compiler, what level of optimization is going on, and you can also set breakpoints in the assembly view, or you can use step in, step out, as we'll see later on in the demo. We also have the option to check memory usage. So there's the overall memory stats, and it's a very key activity in a lot of memory HPC applications. So you can examine this memory across the processes as well. So you can see from rank 0 to rank 2. And yeah, it's both graphical or statistical. There's an option to view everything in a tabulated manner. But yeah, you can the default is to see everything in a graphical sense. When we launch DDT, we get this option to activate memory debugging, and that allows you to have the memory stats. So when you select memory debugging, you will have another option to to select the level of heap debugging. So we have different levels, and we can also add guard pages towards the start or end of your heap. So this heap debugging option, it runs standard checks on the object for stack pointers, and by default, it will be set to balanced. But yes, more arguments are available for checks between quick and thorough. So, but at the same time, the more checking you do, there will be a little more overhead, and it will slow down the process a little bit. When we select this memory debugging, so what happens is we are basically asking DDT to load a debug malloc library instead of the standard malloc library. And this is related with the LD preload mechanism. So for static executables, we would need explicit linking for this. Yeah, so this library will just enable to monitor and instrument heap memory allocation. And with the checks that I mentioned, fast, balanced, and thorough, so these checks ensure memory is utilized in optimal fashion with proper read writes and no overwrites. The hex codes, for example, against certain selected expression in the source code viewer. So they help determine the status of the heap elements corresponding to these flags. And one thing is, the more the number of checks, again, it will slow down the whole process. And there's also an option for custom checks. So you can select 1 or 2 or even more than 10 checks that you want to apply manually. So here we can see the guard pages that I mentioned, each one of them being 4 kilobytes. They are self-explanatory in their name, and so they act like protection to memory allocation. Let's say if you end up giving out of bounds allocation, DDT will prompt you and tell you that this will lead to a seg fault. Each one of them being 4K, so at max you can go up to 32,000. And yeah, it should be kept in mind that the available memory usage overhead is built up by using guard pages, and this would need additional processor nodes or a smaller code sample from the existing sample. Going over to how to launch, it's possible both ways. So you can launch from the GUI from within your operating system, or you can also go with the simple command line flags, where we tend to go with lower optimization flags, O naught. This is just to avoid compiler code generation errors, and it can optimize out certain variables. So these are the flags that you use in GDB when you launch. So you add -G and -O naught, O1, O2, or O3, depending on the level of optimization you want. So to launch DDT, the express launch is just basically typing DDT once the module is already loaded. Or you can add your execution here, and with srun or mpi run, mpi exec, and yeah, you can also you can use -- offline without the X11, and this will go to your HTML report. Then we have remote connect, where if you are starting from login node and the software is running on compute node, yep, you can have the GUI on your login node. And this is how the GUI will appear, where in case of express launch, you'll have the launch window with DDT and map options. And once you will select the run option, the run window will appear with the application pre-selected, and the arguments, you can choose the working directory. You can choose if you want memory debugging, certain environment variables as well. Everything goes into the run window. You can also attach to an existing running application where the debugger gets attached to some desired point in that application. Or you can open a core file. Let's say the seg fault will generate a core dump, and DDT will allow you to view the core file, but the step-in, step-out feature is not available for this functionality. For remote connect, yep, it communicates over SSH. There's the SSH tunnel, and you have to preset all the details to connect to your cluster. And yeah, you can use it either from login node or your local workstation. So yeah, with remote connect, you set up your host name, connection name, your login password, and this is done through the remote launch here. You configure these settings, and it's added to your drop down here in remote launch. And every time you want to do this, you just select your cluster name, your connection name, and you're good to go. A quick look on launching DDT one more time. So you have the module loaded. You can start with your compilation, and once we have that, we can go ahead and launch DDT with, in this case, from your login node or workstation. If you are doing offline, then you can write the report name, whatever you like. So in this case, let's say this is Jacobi OMP mpi.txt. You can also add memdebug flag, so you don't, because it shows up on the run window. If you're going through offline, that is available via the memdebug flag, and you can put some conditions as well for memory leak detection. You can put breakpoints on certain lines with the condition. Also, you can use the evaluate directly from the flag. That's how your HTML report is going to look like, where you'll have information for messages, memory leak report, your output. So it's going to look something like this, with your trace point information and your output. For debugging Python code, there's not much to change. You just have to add another Olinia Python debug flag, and yeah, there will be the same run window. The same for CUDA, where you add the two flags -G and -- CUDA RT shared, and this will show up in your run window. You can select CUDA from here and you're good to go. Very quickly, I'll just show you towards the end a very, very small example. So if you're running something, a typical example of segfault crash here. So we are familiar with this, all of us, I believe, and this is also a very common memory-related issue. So you can see something like this. Most of us are familiar. What happens if you run this with DDT? Instead of a textual information, we have a pop-up where the debugger stops at line 103, where the fault has occurred. And in this case, the reason is mentioned in the dialog box. It's a seg fault, and the address is not mapped to the object, and the program will be paused. The line of code tries to access the memory address that is not mapped to an object. In this case, it's the value of x. So we can see here the two values, and the array tab is actually 13 by 13, so 0 to 12. But the application is trying to write it to 4198, which causes this seg fault. So you can just hover your mouse over the array, and you have basic information about it. And also the variables. So we've seen the essential features of DDT and how to launch, and what are the basic features that are available in the DDT window, some basic principles, and we can now, I think, move on to having a look at how to debug something from your side. Thanks, everyone, and thank you, Florian. Yeah.
This whole thing came around because I was talking with the people at Max Planck about the icon simulations that we are doing at very high resolution, also in the context of EasyWays. And there was an issue with a 10-meter wind speed. And so I looked into that a bit, and I got great help from Moritz, who actually showed me how to use DDT, and also Jeff and Carsten are always around and helping if there's need for something with the tools, or for like we want to run ICON at extremely high resolution and need half a computer for it, then Carsten can fix things for us. So just want to say thanks for that. So this is the kind of simulation we're doing. It's a coupled global 5-kilometer simulation with atmosphere. Here's a low pressure system near Madagascar and ocean currents. Here's sea surface temperature. And if you tell the model that the lowest level in the atmosphere should be 20 meters thick, then you get beautiful garbage data in your 10-meter wind speed. Otherwise, the model runs fine. It just produces garbage in some fields. Now, that's a bit annoying to debug, especially at 5 kilometers. And so I was very happy that René had a setup that runs at 160 kilometers. So we can do the whole thing at like 1% of the resources. We just need 3 nodes instead of 300. And also everything is a lot faster because we're just handling way less data. So with this thing, I could reproduce the problem. So there's this grid cell here in Southern America where things are a bit off. And now to make the debugging easier, you can compile the model with -FPE0. And that means that it traps any errors in the floating point arithmetic. So dividing by 0 or doing other things that don't really work will crash the model immediately. And then while we're at it, we'll also put -0 here. So no optimization, as Suyash told before. No inline, no IP. Some more flags to take out optimizations in the code and make the debugging easier. And then we run the whole thing. And it immediately dies. And the log file already gives us some pretty good hints. There's file surface diagnostics, and there's a function nsurfdiag, and in that function a logarithm is called. And in that logarithm there's a floating point, divide by 0. So we have a rough idea where we could look. And if we look into nsurfdiag, we're happy to see there is a 10-meter wind speed in there, so we're not totally in the wrong place. And there's also some logarithms. But at least to me, who hasn't been doing atmosphere modeling for the last, I don't know how many years, these names are not totally self-explanatory. And so I just threw the whole thing into the debugger, which was really easy. So you take the job script, and the job script has some variable for starting the model. So that calls the srun. You just load the ARM Forge model. So module, we have 1914 that runs on Mistral. And then I just prefix this command with DDT ---- connect, submit, and start ARM Forge on a login node, or in this case, actually, I'll just start it on my laptop, which is a bit easier for me. But it's the same. You could just do module load and DDT on the login node. And I'll try to do this now interactively. We'll see if luck is on my side. So I sbatch the job and switch to DDT. And my job is already running and waiting for me. So yes, I want to accept the connection, and DDT is connecting to the job. Now, basically all we have to do is hit play once this thing has fired up. And the model will run into the crash, and then we can look at things there. So it takes a little moment to start it up. Even this small example is running on 108 threads in the end. 72 of them are atmosphere, 36 are ocean. So the convenient thing about ICON is it's all the same binary, so we don't really have to care too much about atmosphere or ocean threads. But we will do so in a bit. So yeah, things take a little bit. So if you can do small setups, do small setups, but it should be here in a few seconds. Here we go. So really all I do now is press play. And while this thing is running, what I could do is define a group and say process 0 to 71. That's 2/3 of the whole thing is atmosphere, so I could call the group atmosphere 2. I'll just hit cancel because I've already done that here. So here we go. DDT says there's a floating point exception. Divide by 0. Your program will probably be terminated, so just say pause. And I'll just briefly hit pause for all. And now I can look at things. And so we have this logarithm where a divide by 0 is occurring, and the only real thing that could be a divide by 0 is the log itself, which is also what we saw before. So I can now just take this whole thing, copy it, and add an expression to the evaluation. I paste this thing, and now my experience says the underscore WP for working precision is not appreciated by the debugger. And we'll just put the exponential as 2.73 times. And then we see that this is basically 0. And we already see that 14 processes that had a problem here have the same value of 0 in that log. And so now we can look into things. And we could, for example, take this PBN tile, and we get it has a value of 1.94. Add it to evaluations, and we can get this line. And if we just hover the mouse, we see it's somewhere between 1 and 9. Exponential of something between 1 and 9 is pretty okay. Let's see what this is. PBM tile, add to evaluations. That is 100 in all of these cases. So we're doing exponential of something that's around minus 100. Subtract 1, multiply by a ratio. You can take this ratio and add it to evaluation. And it's 1 on all nodes. So let's briefly see what we have here. If my computer lets me. We have the log of this exponential. This exponential has a minus 98 here. Exponential of minus 98 is 10 to the negative 43, so it's a pretty small number. We subtract it from 1, and a round off now makes this turn into a negative 1. So we lost a bit of information here. Multiply with the zero, which is 1. So we still are at negative 1. Subtract that 1 from this one. And we get an exponential of 0. Now there's two things you can, well, there's one obvious thing you can do. That's taking this minus 1 and putting it over here. So you have log of 1 minus 1, and then this exponential. And the model will keep running. Now, technically this works. The question is, are we doing the right fix for the right reasons? And the other thing is this zero, why is it wrong? 1. And Louis actually gave it some more thought, and he solved the riddle, why this whole thing is happening. So thanks a lot, Louis. And I'll just show a few things in the debugger, since it's still waiting here. So I can take this zero and I can just say find. So Command F and then jumping up in the code. So it's ZHUV divided by PCF minus PCS. And ZHUV is a clear 10, so we can search for it again, and it's fixed to 10, so that's a constant. And most likely that's the height of U and V. Now the other guys, PCF, we can also search for that. And we find it's the height of the lowermost full level, and the other one is PCS, the height of the surface. So going back to these guys, it's a different one. Yeah. We can also have a look at the arrays and see PCF is like tens and then a couple other numbers. So probably it's tens over the ocean. PCS is 0, so that's ocean, and a couple of other numbers. So what actually happened was we set the thickness of the layer to 20 meters, but we didn't set the height of the lowermost velocity to 20 meters. With 20 meter model level thickness, we want to have the 10 meter wind speed. And what actually happens is the model puts the wind at 10 meters, so at half the cell height. And so we're interpolating between this 10 meter full level height and the 10 meter wind speed using a logarithm, and that's why things go to the ditch. And in the end, we just shouldn't do an interpolation between 10 and 10 in this way. So that's the clean way of fixing this whole problem. But so I was cheating a little bit when I showed this to you, because if you actually run the model with the floating point exceptions, you get caught in a different error. There is a special second issue, which might be just related to this setup where we're running a 160 kilometer grid with 5 kilometer parameters. And I ran into some self-healing not in numbers, which I just found fun to watch. And you can see a few things about the debugger while looking at them. And there's a little peculiarity about not in numbers. So if you have another number, it's not greater than any other number, and it's not smaller than any other number. So all these comparisons will go to false. And I'll just go back to ARM Forge, end my session, because I need a different binary now. And submit a second job. Go back to ARM Forge. And connecting again. And there should be a new job coming up in the next few seconds. Yep, running. Here we go. So we're doing the same game again, just this time I have compiled the model without the floating point exception trapping. So it would just run over any error that doesn't fully crash it for other reasons. So a segmentation fault would still be detected, but these divide by zero things don't get detected in this setup. Yeah, sometimes it doesn't like me. Not a problem, we can launch this again. So even debugging isn't fully free of problems. So basically what we're going to do now is we'll set one of these breakpoints to the point where I found the floating point error before. And that's in this Magorinsky scheme. So that's like turbulence related stuff. As you can tell from my wording, my background, well, actually my science background was ice sheet modeling, where turbulence isn't really a problem. And now I spent 1.5 years or so at DKRZ. And I'm slowly finding my way into this short time scale, high resolution world. So what we'll do is we'll put a breakpoint in that line of code where the trouble was happening, and we'll make that breakpoint conditional. Because I know there's this HZ0, which is some form of height, and if that thing is below 1, there's an illegal expression. And so I'll just say, okay, if any process runs into this situation, please report that. In standard print debugging, you would put some if-else and a print, and that could also do the job, but this is a bit nicer, I would say. And it allows us to do some really cool things. So we have to scroll down to line 1700. Here. And what I do is I put a breakpoint there, click on breakpoints, and I say this breakpoint gets a condition. So if HZ0 is smaller than 1, and this breakpoint goes somewhere else. And now we play the model. And what happens here is we have a number that's, let's say, 0.9. We take it to some power, which means it stays below 1. We subtract 1, get into negative territory. And then this times 1.5 is basically taking the square root and then to the third power, and the square root of a negative number isn't very healthy, as long as you're in real number world. So we got this breakpoint, we pause everything. And I've already put a lot of evaluate statements here. So hg0 is 0.96. And if I just do one step, we'll see that hg0 now is not a number. The stability function will contain this hg0, will also go to not a number. So we have a second not a number here. And now this little function is at its end, and we'll just step back to where we came from. So I say step out. And I can see that I'm in a different part of the Smagorinsky scheme, where this thing is just evaluated to not a number. We'll multiply it by something and put it into TCM. And now our TCM is not a number, so DDT is highlighting this with like bold and blue that this value has changed. And same for TCN heat, so that actually works. But TCH again has a stability function. This time it's for heat, not for momentum. We can step into that and see what's going on there. So rep is negative something, so we're not greater than 0. We go to the else clause, compute this factor. Again, HDH is below 1, so we will also get another number there for this HDH factor. Here we go. New stability function is also going to be none. And we can step out of this again. So TCH will also be not a number. And then we go into this loop and we compute something that looks like a sensible heat flux, which turns into not a number here. And latent heat flux and BFLX1 and U star, Oberkopf length, inverse, Bösinger momentum. Let's see what happens in that function. So we just step into it. So it compares L against 0, and we see that L is not a number. So we're not in the stable case because not a number is not greater than 0. Not a number is also not less than 0. So in the neutral case, we take the ratio of Z0 and Z1. You see them here already, 0, 10. Ratio of 1 divided by some other constant. That's all safe. So we just computed factor to be negative 0.07. And we can step out of this again. So our inverse Bösinger momentum is clean. And we compute TCH from this and from the same for heat. So this is going to be the same mechanism. And TCH becomes clean again. We get numbers here again on this overview thing. And the second iteration of the whole loop will fix the sensible heat flux and the latent heat flux. And this BFLX and U star and Oberkopf length and all the others. And now I might be curious to see what happens if I actually do all 5 iterations. So I just put a breakpoint behind this loop and say play. And it immediately runs to the end of the loop. So they're still all reasonable numbers. So now that I've seen that this model can actually heal itself, I'm still kind of curious what's going on here. So the whole thing started with this ZMC and ZRUF. So ZMC is 10. Already here, look at the top, it says it's a height to be used as a reference height in the surface layer. Wow, that seems okay. And ZRUF is probably some roughness length. So we can track that up in the code. And we figure it's PZ0M. And I can say view array. And this array is distributed over more processors, so it's across all 71. And I have to tell ARMForge to use the group atmosphere now, so not to ask for the roughness length from the ocean. And yep, pause all of them, see what happens. And we get a table with a lot of, well, we don't really have this now because our process is in a totally different part of the code already. That's a bit of a shame, but I can go up in the stack. And now I'm in process 9. So when I selected the group atmosphere, DDT decided that I probably wanted to look at process 0 now. And I can just look at the logbook and see that, for example, process 19 was one of those that I looked at before. So just go to process 19, and I'm back here. So I click on this P0M, PZ0M, and check it up a bit, and it says it's an aerodynamic roughness length that gets into this function, subroutine exchange coefficient 3D. Hallelujah. And it's about variable 10-ish in this call. And now I can go up in the stack and say, okay, it's called here, and variable about 10-ish is PZ0M tile. And see what's happening here. It calls it different with the same. Going up further, going up further. Okay, it's also saying it's a roughness length, but now we're higher up in the stack, so we can see who called whom. It's not just like who could have called this, but this is the way we were called. Icon was called, and Icon called. Well, Atmo model and hydrostatic and all these things. And we can give the whole thing a try again at a higher level. So maybe the other processes are all still stuck in this function. And we say, yep, 271. And we can say evaluate, and we're way more lucky. So let's see if we can actually visualize this. Yes, just do it. And we get this nice 3D view of this roughness length across all processes of all processors. And we can already see that it's somewhere everything is related to column 3. The other columns are pretty clean, but column 3 has a roughness length up to 20. And that's, of course, greater than the 10 that we were comparing it to earlier. And the other thing I can do is I can actually export this whole thing to netcdf, which I was a bit surprised that it works, but it does. So we just call it HDF5 and say this is my array. Save it. And I have this random directory on my laptop where things go that are not backed. And so we have the myarray.csv, and I can do ncdump -h on my array. And I have a completely standard netcdf file. I would have used different names for the variables, but that doesn't really matter. So I can use nckS. Yeah, I can use ks -3 in C and create a standard netcdf3 file. I could do nseries name dimension dim0 time to make the whole thing CDO compatible. And I have something I can look at with CDO or any other thing we're used to. This I found pretty amazing. I just found it today. The other thing you can do is, so this is all shaped, this array is basically 4-dimensional in the memory, but we've fitted into a 2-dimensional table but we can choose which of the index numbers goes into which part of the table. So we can set it to columns for table 2, evaluate the whole thing, visualize again. Yes. And we can see that in the second index, the issues are in indices 0 through 6, and the last 3 are safe. So I still don't really know what is going on there because I'm not in this atmospherics code piece. I'm not very firm there, but I can get a lot of information on the code.
You could have. You can also have a look at the statistics in the multidimensional
array.
Let's
do that. Yeah. So I can do statistics, and I get information like I have 93,000 numbers, and they have a sum, a minimum, a maximum, a range, mean, variance. And that actually also works for this array, which is pretty nice. So it takes a little bit longer. And I think that's partly due because a lot of the processes don't have it, and the system has to figure out which actually have it and which don't. But it will also show me the statistics for an array that's only partially available. Just as the little spark lines it does next to the variables, they also work. If there's like 15 processes that have your variable, they will be shown. So you can already get ideas. Yeah, well, statistics here are not that useful. I had better ones. But I really like how you can just like walk around in the code, go up in the stack, go down in the stack, go through something where you're like unsure what it's going to do, look at it step by step. This is basically the things I wanted to show you. If there is a problem, feel free to contact us at DKRZ, so Beratung or support at dkrz.de. And in general, if you can reproduce a bug in a small setup, go for the small setup. It makes your life a lot easier. And if you're running the big model or so, maneuver yourself as close to the crash or problem as possible. So if you have the choice between putting a restart to day 3 of your simulation or spending 2 hours of running before the bug happens, put the restart to day 3 and work from there. As I showed before, compile with FPE0 to catch division by 0 and friends helps a lot in finding things when things are strange. And the debugger that we just showed can provide a lot of insights into code behavior. It won't fix all the problems you have, but it will help you find a lot of them. And if it's a crash in a big run, please feel free to contact us. We have DDT, we have other tools. And we can also work with reservations to avoid queuing times. So that's one of the reasons why my jobs went through that fast now. I simply had the option of skipping the queue. That's it from my side. Let's see if there's any other questions. No. Thanks a lot to Suyash and Ryan.
Thank you, Florian.
And thanks everybody for watching. We will have another tech talk in 2 weeks featuring our new data storage, well, the new tape archive system or the new front end to the archive system. So stay tuned for that. And if you have any other suggestions what we should present about, or if you want to present something even better, feel free to contact us and we'll find ways to do things. So thanks a lot, everybody.
Thanks, everyone. Thanks, Florian.
Sure. My pleasure. I learned a lot. So you can even present about things that you've just started to learn if there's good people that are having your back.